Just like light has properties of both waves and particles, it's been found that electrons do as well. So Louis de Broglie discovered that particles could have wave-like characteristics as well. He predicted that the wavelength of that particle is inversely proportional to its momentum. So it depends on the speed and the mass of the particle as well. Because electrons are so tiny, the wave characteristic of those electrons is significant. So this does apply to all particles. You could find the wavelength of a baseball if you wanted, but because it's so large, the wave properties are not significant. But electrons, because they're tiny, it is significant. And so if we wanted to calculate the wavelength of a particle, it's equal to Planck's constant, h, divided by the mass times the velocity, which is also the momentum. So how do we go about proving that electrons behave as waves? Well, we can do the same thing that we did with light, where we pass a beam of electrons through two slits to see if an interference pattern is produced. Remember the light bright, or the light dark that we saw with the light? We can do that with electrons. So if it behaved as particles, the particles would pass straight through the slits, and there would only be a detection of the electrons directly behind the slits. However, if it behaved as waves, we would see an interference pattern where we have the bright spot that falls directly between the two slits. Well, the interference pattern is what is observed. So we know that electrons behave as waves. The really interesting part is that if we turn that electron source down so that only one electron is being emitted at a time, we still see the interference pattern. So somehow the electron is passing through both slits simultaneously. And this is what leads to the quantum mechanical model of our atom. So quantum junction, right? So because behaving like an electron, it can actually get in two lanes at once. Okay, I'm sorry. So we do have, this leads to complementary properties. So if you've ever heard of the Heisenberg uncertainty principle, that is explaining complementary properties. So we can observe the wave nature of the electron, the interference pattern, or we can observe the particle nature, but we cannot observe both at the same time. So the particle nature would be represented by the position, which slit it is passing through. So the wave and particle properties are complementary. The more we know about one, the less we know about the other. So the more that we know about the wave nature, the less we know about the position of the electron as it's traveling through space. The more we know about the position of the electron, the less we know about it behaving as a wave. So there is an experiment that proves these complementary properties. If we take and we put a laser behind the two slits that we're passing the electron through, because the laser would allow us to see a little flicker in light as the electron went through one slit or the other. As soon as we try to observe it, the electron behaves as a particle. It passes through one slit or the other, and we no longer see the interference pattern. So just the act of observing it forces it to behave as a particle. Not only are the wave properties and particle properties complementary, but also the energy of the electron. So for the energy of the electron, and its position, these are complementary properties as well. So the more we know about the energy, the less we know about the exact position of the electron in the atom. So the best that we can do is describe a highly probable region of finding the electron. And we can do this through solving the Schrödinger equation. So because the properties of atoms that are really important to us, like how they bond and how they interact, are related to the energies, this is the most important property to know more about. Exactly where the electron is found is less important to chemists.